Okay, that should do it, right? That should do it. Alright, so today I'm going to be learning Clojure. And I'm going to start by putting on some music. I want it love, don't need it love. Most of all, most of all. So, below are some examples of literal representations of common primitives in Clojure. Maybe I should start with the YouTube video, actually. What can I do?
Well, hello Internet, and welcome to my Clojure video tutorial. In this one
Clojure.
tutorial, I'm going to cover the core syntax of the entire language. In the description underneath the video, you'll find timestamps to all the individual parts, so you don't have to watch everything all at once, or you could just use this to look for specific things you're interested in. Also in the description underneath the video, I have a link in which I show how to install both Emacs as well as how to set up the whole entire Clojure system I have right here. Of course, you don't need to use Emacs with Clojure. Everything I cover here is going to work with any editor, but I just thought I'd use that because it's used everywhere else. And I have a lot to do, so let's get into it. Alright, so here is Emacs, and what I'm going to do is I'm going to start off by creating a project, and I'm going to use line and gen to create said project. And how you do that, this is just in a regular terminal, and this would work the same on a command line if you install everything that I have set up here on Windows or Linux, of course, or anything else. So what we're going to do is I'm going to go line, new, app, and what do I want to call this? Let's just call it tutorial. That's quite simple. And all that's going to load up, and there we go. And I can then come in and change directory to tutorial.
Who becomes a Twilio developer? People who code as a side hustle. People who lead.
And then we can see all the different things we have here. And I'm going to change my directory to the source directory and then to tutorial. And there we are. And there is the core Clojure file that we are going to be putting all of our code into. And how we go and open that, in Emacs anyway, is down here. You're going to see I'm going to go Control and X and Control and F. And I'm going to type in core.clj. Hopefully you can see that. If you couldn't, view it full screen. And you can see here, I'm going to go Control X and Control and increase the size of my code here on the left side. And then I need to decide what I'm going to do. I'm going to go CX and O to jump over to the terminal side, and I'm going to be running all the code, some code on the left, some code on the right, and so forth and so on. Now to get the code here to start executing, I'm going to go MX, and then I'm going to type in cider-jack-in. And you can see that everything came up here on the bottom of the screen. CX and C++.
I feel like I've missed so much already.
CX and O, jump over here and go CX and 0 to close that. So why don't I just have the code on the top and then run everything in the bottom. So we can just go and increase that a little bit more. And there you go. You'll be able to see all that. All right. So up here at the very top, I declare a namespace. And just like all namespaces, it's just going to provide a unique name for my functions. And on the next line, we have basically our Clojure files are going to run on the Java virtual machine. So we're going to need to define a class, and we do that. And execution is going to start in the main file that we have right here. And I can jump down to the bottom of the screen. Well, I'm actually there already. So I can just do this. And to run main, I can just go and put parentheses and a dash and main and parentheses, and you can see that hello world executes down
Define.
there. So first thing I want to talk about is variables. So variables are going to be immutable inside of Clojure, which means the value cannot be changed.
I feel like this is maybe even a little bit.
Hello all, and welcome to the 5th FunkProg Sweden. We're so happy that this time we are live from a TV studio actually in Stockholm. So we don't have any audience, we just have the speakers and some studio people here. So welcome all on the YouTube. So the agenda today, I'll do a short intro, that's what we're doing now, and then we'll do a presentation on Clojure in a nutshell by James Trunk. And then we do a second presentation, Polylith, the last architecture you will ever need by Joachim and Furken. And then last guy up is Emil. He's going to talk a little bit about Rust and what Rust borrowed from functional. Yes, so why did I start this community? FunkProg Sweden, because we love functional programming. We're open and inclusive. We want to spread functional, so everyone will do functional programming in the end. We also like to share, hence we are here and hence we're streaming to you over YouTube. So let's have fun and spread functional programming. And speakers and sponsors. If you have anything to present around functional, it doesn't need to be in a functional language. We had Harald from the C++ community coming over and talking about C++ and what it does in functional programming, so please come. Also, if you have a venue you could share once the Corona madness is over, please come to us. So just contact me and reach out to me, Magnus, or the other organizers, Tien and Matthias. And last but not least, how to today as we live stream. Please ask any questions in the YouTube chat that you have, and we'll send it over to the presenters. So let's start. So I will introduce Clojure in a nutshell by James Trunk. Welcome.
Thank you very much, Magnus.
You're warm welcome.
I'll take that from you.
Yep.
See if the technology works. Hi, everyone. Hopefully you can see the slides now. My name is James, and I'm here to give you a brief introduction to Clojure. And we're going to start by exploring Clojure through the lens of the design philosophy that is behind the language. And that's because I found that understanding why something is the way it is often gives a lot more value than just understanding what it is or how that it works. And then once we've done a little bit of that philosophical discussion, we'll finish with a little bit of live coding. I'm a bit nervous about that, but we'll see how it goes. And the idea there is to put some of the theory that hopefully you've been learning into practice and give you a little bit of an impression of what it feels like to create solutions with Clojure. Okay, so let's dive in. So design is separating into things that can be composed. Rich Hickey, he's the creator of Clojure, and I think this quote is perhaps the perfect place for us to start in our journey of trying to understand Rich and how he thinks, and especially his creation. And what I think this quote tells us is that Rich really values separating ideas that should be untangled, but giving us tools that allow us to combine them back together into simple solutions. So let's have a look at how he puts that into practice. And the first idea we're going to cover that Clojure has as a base philosophy is that it separates data from functionality. It does this by elevating data to a first-class citizenship within the language, and it encourages you to build your solutions using pure functions that work on that data. You could say, in a way, that Clojure is the antithesis or the opposite of object-oriented programming, where the fundamental idea there is to tangle up those two concepts of data and functionality into objects, whereas Clojure wants to split those apart. But why is that? When you combine two pieces of data, you get data. When you combine two machines, you get trouble. If you only remember one thing from my talk, I really want it to be this quote. Write it down, take a screenshot, ask Siri to take a note for you, and then promise me that you're going to come back later and reread this and just give it a couple of minutes to ruminate on it, to ponder it, and think about why Rich is right here and why this is quite a profound way of thinking differently about writing programs. When you understand this idea, then you'll understand the brilliance of promoting data up to the syntax level of your language, and then why giving a huge toolkit of functions to work with that data is the right way to do things, and that's exactly what Clojure does.
Damn
Let's
ads.
explore your future with Udemy.
So let's have a little look at how does data as syntax look like. So here are the 4 core data structures that Clojure offers: lists, vectors, maps, and sets. And as you can see, lists have the syntax of using parentheses, vectors, square brackets, maps, curly braces, and sets have a hash in front of the curly brace. And you might also notice that there are no commas separating the elements. That's because in Clojure, a comma is treated as white space. So that means it's fully optional if you put it there or not. Most coding standards or guidelines would recommend not to put it for lists, but to use them just as a visual separator when you have key value pairs in maps, as you see here on the 3rd line.
Makes sense.
So what does this mean when we have data as syntax? It means that we visualize our data, we bring it to the forefront, and it makes it easier to think about, to talk about, to communicate to each other, and to work with. Not only that, but it also makes it easier to construct nested data, which is of course the main kind of data that we work with our systems. Here we have an example vector that contains 3 maps, and each map contains 3 key value pairs, and one of those values, and to work, comma is treated as white space.
Yeah, vector
so that means
with the
that
map.
we visually work with. Not only that, but it also makes it easier to construct nested data, which is of course the main kind of data that we work with our systems. Here we have an example vector that contains 3 maps, and each map contains 3 key value pairs, and one of those values is a vector itself. And what I want you to notice is how clearly we see the shape of the data, and think about how hard it is to see the shape of data when you're using the program, when you're using code to construct rather than syntax. You just don't see it, right? It's lost in the code. I think there's a reason why JSON has taken over the world in terms of communicating data. And you can think of Clojure's data syntax as JSON with superpowers. One of those superpowers is that Clojure's code itself is data. So Clojure doesn't stop with making the system data easy to visualize and to reason about and to work with. It takes the perhaps heretical, but I believe inspired next step to represent the code itself as data, as a data structure. That's because Clojure is a Lisp. Lisp stands for list processor. So you can probably guess which data structure it uses to represent its code. That's right, it uses lists. And here's how a function call is represented as a list in Clojure, where the function is always the first element in the list, and the arguments are the rest of the elements in the list. And this is called prefix notation. And what's good about it is it simplifies the syntax, because it means that the language is 100% consistent in the order of precedence. There's no book that you need to learn that in this case you put the operator or the function here, in this other case it goes there. It's always at the front of the list. So let's see some examples of how that looks like. So when we want to add numbers together, you put the function at the front of the list. When we want to find the max of a group of numbers, you put the function at the front of the list, and the arguments follow. And of course you can have as many arguments passed to these as you want. When we're filtering a collection, here we use a predicate function called odd that filters out the odd numbers from the vector. Again, filter goes at the front, and then you pass, in this case, a function as the first argument. And then when we're doing conditionals, it's the same. If goes at the front, then we have a nested list. That's the important thing to notice about this piece of code. So the way it works with Clojure is when you have nested data structures in the code, so nested lists, you always evaluate from the deepest nested list first. So here would evaluate that 1 is less than 2, so it's true, that predicate. and therefore this conditional will return A rather than B.
Why should you use Miro? Well, when you draw on a whiteboard, no one sees it. With Miro, you plan together in real time.
Okay, here's another quote. Nobody wants to program with mutable strings anymore. Why do you want to program with mutable collections? You've probably noticed already that I like quotes. That's because I think at their best, they have an almost magical ability to distill a lifetime's worth of wisdom and knowledge into a bite-sized piece of clarity. And I think the particular insight with this quote is that Rich is saying we've already solved how to make our programs stable to build upon. And the answer is building on immutable data. And in Clojure, all the collections are immutable by default. And I think this is something that our industry has started to wake up to. Of course, you get immutable data structures in most languages now. But where I think Clojure is different is that it did that right from the beginning. It's a core part of the language, and it's not been added as an afterthought or as a library. So that changes how those data structures are and how people code by default in Clojure in a good way. So let's get a feeling for what it's like to work with these immutable collections, starting with strings. So here what we're doing is we're defining a string with the name first name, and we're giving it the value Dave. And as you see, it's in the list, and def is how you define, and that goes first, and then you pass the arguments just as before. So you already understand Clojure, right? That's kind of cool. And then if we're going to manipulate that string, so in this case, we're concatenating it with another string, I'm sorry. And that outputs I'm sorry, Dave, as expected. But we haven't changed first name. The value of first name is and always will be Dave. And that's pretty common in most languages. That's how we do strings now. Mutable strings aren't really a thing. But where Clojure is different is all of the other collections working just the same way. So here's an example where we've constructed a vector with 3 elements. We've called it ages. It has 3 integers in the vector. And then when we conjoin a new element onto the end, 21, that outputs a vector, but it's a new vector, just like we had a new string. And if we look at what's in ages, it hasn't changed. And that gives us this stable base to build upon. It means that there's not the shifting sand of mutability underneath everything that we're building.
That's always okay.
So what does Rich think the problem with mutability is? So eventually, with mutable objects, you create an intractable mess. And encapsulation does not get rid of that. Encapsulation only means, well, I'm in charge of this mess. So what have we learned so far? Clojure separates data from functionality. Clojure visualizes our data. It brings it to the front. It makes it a first-class citizen when we're working with our code. Clojure code itself is data, and Clojure collections are immutable by default. And all of these 4 properties combined are normally what people mean when they say that Clojure is data-oriented. What it means is Clojure puts data front and center when we're building our systems, when we're writing our code, when we're talking about it with our fellow developers, and it changes the way you think about building systems, and it enables us to build fundamentally simpler solutions. Okay, so that's the basics of Clojure's design philosophy. But before we hop over into the live coding part of this, I wanted to teach you a couple of pieces of syntax, just so it's easier for you to follow along if you haven't seen Clojure before. So here, we're defining a function called greetings, which takes a single argument called name, and it concatenates it after the string hello. And you'll see that this looks very similar to when we were defining values. You define functions in essentially the same way. However, because creating functions is so common when you're writing code, right? Well, that's what we do for the most part when we're writing functional approach. Clojure actually has some syntactic sugar to simplify and shorten and reduce the nesting for when we're making our functions. So this is the exact same definition, but here we're using def-n instead of def. And you can think about reading that as define function instead of define. So it's def-n greetings name, and then the same implementation. So what we've essentially done is shortened how much we need to read and understand each time that we define a function. So that's good to know because we'll be defining some functions later. And then using that, you already know the rule, right? You put it in a list, the function call goes first, then you follow it with the arguments, in this case a single argument, and it would output hello Dave. So our custom functions are treated in just the same way as the core functions in the language. I think one of the things that can be a little bit upsetting when you're first reading Lisp code, and Clojure is no different as it is a Lisp, is when you get quite a lot of nesting going on in the code. So this has 3 nested function calls. And how you would read this is, like I said, from the inside out. So we'd start by evaluating range 5, which would give us the sequence 0, 1, 2, 3, 4. Then we apply the increment function with map. So we map it across each of the elements in the sequence, giving us 1, 2, 3, 4, 5. And then we filter using the odd predicate, so only letting the odd numbers through in the end, which gives us the output 1, 3, and 5. But it feels a little bit unnatural, especially when you're getting used to reading code that way. It feels a bit, oh. And I think that's because, in English at least, that's not how we think and read and write. We tend to read left to right, not right to left, and we tend to read top to bottom. But Clojure has a trick up its sleeve, a trick that is called thread last. And thread last is a macro that changes the order of the code essentially and lets you flip it. And it's an arrow with 2 heads. You see it here. This is a ligature version, but it's just a dash with 2 chevrons. And what happens here is we can put range 5 first. We see the output, like I said, 0, 1, 2, 3, 4. Then that gets piped or threaded into the next function call in the last position. That's why this is thread last. And then finally it gets threaded into the filter at the end. And if you haven't seen this before, it might be a bit confusing, but if you've ever used Unix, you might know the pipe, when you pipe the output of one command into the input of the next, and that's essentially what we're doing here. It's called thread, but it's essentially the same. And like I said, commas are treated as white space, but the output of executing range 5 gets placed into where those commas are on mapping into the last position, and the output of mapping into the last on filter. I hope that makes sense, because we're going to use this quite a bit.
At Full Sail, our technology programs are designed with a different approach to learning.
Great, one last quote. Systems are dynamic and data-driven. It might be a nice idea to use a language that is also dynamic and data-driven. So I want to show you what it feels like. Of course, we're not going to build a whole system, and we're just going to do a bit of noddy examples, really, but it still hopefully will give you a feeling of those properties that we talked about, the design philosophy behind Clojure. How does that impact when you're working with code and shaping algorithms? So let's jump over and do that. Let me just flip into mirror mode. Excuse me 1 second. Okay. Live coding, not terrifying at all, right? So let's see if we have the REPL up and running. So we will send +1, 2 to the REPL, and we get 3 back. Shall I zoom in a tiny bit more, maybe, just so it's even easier for you guys to see? That hopefully is big enough. If you're watching on a mobile phone, then I'm afraid you only have yourself to blame. Wait until you get home and watch it on the big screen. Okay, so what's happened here? Like I said, it's a list. The first element is the function, then we pass the arguments, and we're returning 3, right? That's nice and simple. But what I'm going to show you in this example is some textual analysis. So what we're going to do is we're going to define a book, and we're going to read in a file.
You're going to put nest.
And one of my favorite names functions is a function called slurp. I just think it sounds so delicious. And we're going to slurp in a book from the Project Gutenberg. And it's quite a big book, so we'll see how long this takes to load. And what slurp does is it reads a file either from the local file system or remotely, as you see here, and it converts it into a string. So we've now set the value of the book symbol to be a string of the book. If we're going to do some analysis on it, we're going to want to break that out into the words in the book as a separate sequence. There are a couple of ways we could do this. One way is to use like string functions and split them based on spaces. In fact, we're going to do a regular expression. There's a function called reseek that does a matching pattern and outputs a sequence that matches that regular expression. And I don't know if you've ever heard the phrase, but if you have a problem and you solve it with a regular expression, now you have two problems. So that's basically what we're doing here. So what we're going to match it on is word characters or quotes. So anytime we see an A, B, C all the way to Z, or a 0 to 9, or I think underscore, that's a word character, and any quote or apostrophe, so that we get possessives. And let's run that across the whole book. Hopefully that will work. Okay, and let's count how many words we have, and that might give us an idea about what book we're looking at. 220,391 words. If someone knows what the book is just based on the word count, I will be impressed. But let's take the first 20 of those words, and that might tell us what the title is. So, it's Moby Dick or The Whale by Herman Melville. So let's do some analysis on Moby Dick. So the first thing we're going to try and find out are what are the 20 most frequently used words in this book. And we're going to use the thread last macro, the one that I just explained to you what it is and how it works. So hopefully you can follow along. So we're going to take the words. And there's another really useful core function that's called frequencies.
I don't know about today.
In Clojure. And if we read the text, it's a bit small here, but it says, returns a map from distinct items in collection to the number of times they appear, which sounds almost exactly like what are the 20 most... It's Moby Dick or The Whale by Herman Melville. So let's do some analysis on Moby Dick. So the first thing we're going to try and find out are what are the 20 most frequently used words in this book. And we're going to use the thread last macro, the one that I just explained to you what it is and how it works. So hopefully you can follow along. So we're going to take the words. And there's another really useful core function that's called frequencies in Clojure. And if we read the text, it's a bit small here, but it says, returns a map from distinct items in collection to the number of times they appear, which sounds almost exactly like what we want. So let's run that. That might take a while because it's a big book. So here we've got a map, and it's the word and then the frequency that it appears in the book. And I already see a problem here because lower is ironically not lowercase, it's uppercase. So what we're probably going to want to do is use Clojure.string / lowercase. So this function takes a string and outputs the lowercase version of that string. But of course, with words, we have a sequence of 220,000 strings. So we can't just run this once. We have to map that function across all of the entries in the sequence. Let's see if that fixed our problem with uppercase. Yeah, that looks good. And like I said, when I briefly introduced functions, but this is what's called a higher order function. So what happens is, functions as well can take data or they can take functions. So this is a higher order one that takes the lowercase. Okay, so now what we want to do is we want to sort this so that we can figure out which are the most frequently used ones. And if we just do a standard sort, it's going to sort them alphabetically. So we want to give it another function to sort by. And because we had a map, we know we have keys and values. So if we sort by keys, it's going to sort alphabetically. But what we're going to do is sort by the value, because the value was the frequency. So hopefully this will give us, in order, yes, so these are the words that only appear once. And then the last ones of this list should hopefully be the most frequently used ones. So let's take the last, say, 20, because that's what we were aiming for. And here are the 20 most commonly used words in Moby Dick. However, these are very, very boring because these would be the 20 most commonly used words in most English works, especially at this length. So what we're actually going to do is try and make this a bit more interesting. We're going to define a value called common words, and it's going to be the set of common words in the English language. And I had prepared that one earlier, so we paste that in. And here you start to get a feeling for what it's like when you bring the data and the data structures up to the front to be first class, because we see the shape of this data, right? Okay, so now we have those common words. So what we want to do now is, after we've done them lowercase, we want to remove those words out of the collection, common words. So let's run that, and hopefully we'll get a different result. Yes, this looks promising. And what's happening here, maybe this is interesting. How did it work that we could pass a set into the remove function? So let me just take a quick detour to explain what's happening there. When we have a set, so let's say we have a set that contains 1, 2, and 3.
Oh, this is gonna take a bit. Alright, I need to take a quick nap.